Hello and welcome to today's digital replay. We're continuing our discussion of geology, and now we're talking about plate tectonics. So we briefly touched upon the fact that there are these lithospheric plates on the Earth, and we briefly discussed that they have boundaries or edges, and we also briefly discussed that they interact with one another, and there's different kinds of boundaries, convergent, divergent, and so forth. So now we're going to go into the who, what, where, when, and why of this whole plate tectonics thing. But to do that, we've first got to start with this guy, Alfred Wegener, this German, who was like an all-around incredible person who did a lot of different things with his life. But mostly he was interested in climatology. He was interested in weather and climate. He was actually one of the pioneers of using weather balloons. A very fascinating guy, had his feet or fingers in a lot of different projects. He did a lot of research out in Greenland, did a lot of hiking around in the most remote parts of the world, and one time he was sick and he was laid up in a hospital and not doing so good, and he started to think, and he was looking at a map of the world, and he noticed that South America and Africa kind of looked like two pieces of a puzzle. And I know you've probably thought about this when you were younger and you used to think about things, but he started to wonder, I wonder if they are two pieces of the same puzzle. So he went out and did some research. And in his research, he started looking at fossils, because fossils are good evidence pieces, good pieces of evidence. And he found some similar fossils on different continents across the world. For example, he found Cynoganthus fossils, this organism here, on North America and South America, which makes sense because there's a land bridge between those two continents. But he also found some fossilized evidence of Cynoganthus in Africa and Eurasia. Through more research, he found Lystrosaurus, this kind of funny organism here that lives in warmer climates, and he found it not only in warm climates, but also fossilized evidence of Lystrosaurus in Antarctica. So fossilized evidence of a warm climate organism in a cold climate. There's also evidence of the Mesosaurus, this sort of aquatic organism here, on both South America and Africa, and a fern called Glossopteris on basically every continent, even Antarctica. That led him to wonder, why? How did these things get here? Well, the accepted theory at the time was that there was some network of land bridges between the continents. So the thought was that there was these complicated network of land bridges between all of the continents, and perhaps that's how the organism traveled from one continent to another. But Wegener didn't accept this theory, and he started thinking, what if all of the continents were not separated? What if at one point they were all together? And so when he mapped out where the fossil remains were found on these different continents, and then started to put these pieces together as if it were one giant continent, he found that they fit perfectly across. Notice how perfectly that fits, as if this was one continent and these organisms just lived in this area on the continent. But he didn't stop there. He started to look for more evidence. And he started to look at the rocks, because rocks tell us a lot about what's going on in a region. So he started to look at what kinds of rocks were in areas and comparing them to the rocks in other areas. And specifically, he looked at geologic landforms, like mountains. Let's just give the example of the Appalachian Mountains. If you compare the rock type and the age of the rocks in the Appalachian Mountains, and you compare those to the Atlas Mountains in Africa, in northern Africa, Morocco, what you find is that these are the exact same rocks from the exact same time period here in North America as they are in Africa. Now we can go even further and we can look at some mountain ranges in Norway, in Great Britain, and in Greenland, and we find that these are all similar rocks from a similar time period. This mountain range was one and the same. It was all connected. So perhaps this, and this was part of one large mountain range when you pieced it all together. Then he started looking at other pieces of geologic evidence. Now, when we were talking about ice ages, we talked about the evidence for the ice ages being glacial striations, or carved out grooves made by glaciers. We find those glacial striations in very warm climates. South America, Africa, India, Australia. These glacial striations exist on rocks in places where it is currently not cold. Perhaps once this was a colder climate area. Perhaps once this was in a different spot. Wegener's theory of continental drift claimed that the continents have and are continuing to move. He had no idea the process for how these things were happening, but he had lots of evidence to back up his thoughts. In your notebooks, I asked you to write down Wegener's claim and the evidence and reasoning he gave for why he thought these continents were moving. Not the process or how they were moving, but why he thought they were moving. That's what I asked you to do in your notebook. And then we went through and we talked about evidence that the continents are actually moving, that we can actually see by looking at the different boundaries between the plates. Now you can find the table for this on the website, on the class website. You can find the table that has all of this information that we filled out in class. So you can find that table on the website if you didn't get it complete or you need help finishing it. But I'm going to go through each one of those items on that table so we can see the evidence that we now know, that we now can look at and know that the Earth is actually moving, that the lithosphere is actually moving. The first one I wanted to talk about was the transform plate boundary. So this is where two plates meet and are just moving side by side. And if you have two continents meeting and moving side by side, you do not have volcanism. No volcanoes here, but you have lots of earthquakes. Very shallow to medium earthquakes through a broad region. So we have lots and lots of earthquakes in this region. This is an example of a good continental transform plate boundary. So here's the plate boundary here, and we actually call it the San Andreas Fault. This is the boundary here. And as this plate, the Pacific plate here, is moving, and the North American plate is moving, they're moving in opposite directions. So they just kind of move parallel to each other. But notice that it's not a straight, smooth line. There's lots of bumps along the way. And that causes a lot of friction. Even at the smaller level that we can actually see, it causes a lot of friction. And this friction is what moves the Earth. It makes earthquakes. So we have these plates moving past each other. There's lots of friction. It gets stuck, and then some of it breaks free. And that breaking free and that friction, that breaking free, that's where you get lots of earthquakes. So again, no volcanoes, but lots of earthquakes. The ocean versus ocean transform faults. This is very rare volcanism. Very rarely do you have volcanoes at these fault lines. But you do have earthquakes. Very shallow to medium depth earthquakes here in this kind of region. Now notice that I've given the example of the Cane fracture here at the Mid-Atlantic Ridge. So the Mid-Atlantic Ridge is actually what we know of is what we know of as a divergent zone. Okay, so this Mid-Atlantic Ridge is a divergent zone, but divergent zones aren't just a giant crack in the Earth that move apart. It's going to crack at specific locations, and then it's going to fracture or have these transverse faults at other locations. So like a zipper, it's not just going to open up. We've got some places where it does overlap, and you have some moving in opposite directions as the plate pulls apart. So these transverse fault lines in these divergent zones, these are transverse fault lines because one part of the plate is moving this way and the other part of the plate is moving this way. So we have this movement in opposite directions, side by side. We have a nice fault line created. Again, lots of earthquakes, shallow to medium depth earthquakes, but very rare volcanism. Next examples that we talked about were both the divergent boundaries. So we can have divergent boundaries in oceanic crust and also in continental crust. So the example for the continental crust that I gave was the the Great Rift Zone, or the Great Rift Valley in Africa. And what we have is this part of the plate, the Nubian African plate and the Somalian African plate, and they're separating. They're going opposite ways. And as they go opposite ways, they're tearing a hole. They're ripping this part of the plate apart here. Right here, this part of the plate. Now you can see that there's already starting to be water gathering in these lower elevation parts. This is all going to be newer crust down below here as we rip this plate apart. And eventually it's going to all be so low that this will all be ocean flowing in here, and then this will be a new island ripping off of there. Wouldn't that be cool? That'd be pretty cool. I mean, this is my guess. This is what I envision happening. Will it actually happen? Hey, time will tell, right? So the African Rift Valley, yes, absolutely, there's going to be volcanoes, lots of volcanoes through here. Look at all these little red triangles, means volcanoes. It's because we're making new crust here. We're tearing this apart, and the basaltic, the rising mantle through the thin crust is going to flow out onto the land, and we call that volcanoes. Is there going to be earthquakes? Absolutely, there's going to be earthquakes. These very shallow earthquakes, not very deep. There's lots and lots of earthquakes throughout the region, throughout the area where this earth is moving and building new earth. For oceanic, we have lots of divergent zones to choose from. I chose the Mid-Atlantic Ridge, and I specifically chose the area around Iceland because what you have is the North American plate and the Eurasian plate moving in opposite directions, and they've diverged enough that enough magma, enough basaltic lava has flown out of the fissures and made a new island, made new land. We've had enough flow out of there to make new land. So this is a divergent oceanic crust zone. Lots of volcanism, lots of very active volcanoes, very shallow earthquakes. It's a really, really active area. Really, really cool to see all of this lava just flowing out, creating new Earth. Convergent zones, we're going to talk about 3 different convergent zones. The first one I want to talk about is what happens when you have 2 continental plates collide, or you have 2 continental crusts collide with one another. In a continent versus continent, the example I give is the Himalayan mountains. This is a perfect example. We had the Indian plate slam really hard into the Eurasian plate. It's continuing to move into the Eurasian plate. You have these 2 battling continental crusts. Both are hard-headed and don't want to give. And so what ends up happening is you have this folding and this smashing and this metamorphism of these rocks, building these giant mountains, really, really high mountains. These very young mountains, these are really quite new mountains, tower into the sky, but are not volcanoes. These are not volcanoes. This is sometimes really hard for us in the Pacific Northwest to understand that there are mountains that are not volcanoes because we have so many volcanoes in our backyard. But where 2 continental crusts collide, you have no volcanism. You just have this intense metamorphic rock formation as these 2 crusts battle it out to see who's going to win this fight. Again, lots of earthquakes. We're going to have lots of earthquakes throughout this. Lots of earthquakes from very shallow to very deep as these 2 continents battle it out. But no volcanoes, none at all. Now in the ocean versus ocean collision, so here you have oceanic crust colliding with oceanic crust. In this collision, you are also going to have earthquakes, but you are going to have volcanism. If this looks familiar, this should look familiar. This is the top part of something called the Ring of Fire, which is the ring around the Pacific Plate. Around the entire Pacific Plate, we've got these volcanoes happening. This is called the Ring of Fire. So yes, there's volcanism when we have the ocean versus ocean collision. And again, this ties back to what is oceanic crust made out of? Well, it's this basaltic, very thin crust, and you have this water mixing, and you have this thin crust, and boom, you're going to have some volcanism, some very basaltic lava coming out. And so we're going to have some volcanism. So an example is that we're going to have this the Aleutian Islands here, and this Aleutian Trench. So here we're getting these islands formation because of this collision between these oceanic crusts. So this is a really good example of that. Now the very last one is the convergent boundary, and it's continent versus ocean. Now this is where it gets exciting because finally we are talking about something that's happening right here in our Pacific Northwest, right? We're talking about this subduction zone. Now you've learned about subduction zones in practically every class since middle school that has talked about geology. So you should already have a pretty good idea about what a subduction zone is. But for our class, when we're talking about the Pacific Northwest, we know that, especially in Washington, we do not have a perfect looking subduction zone. Something else is going on. Because here in this subduction zone, we have the subducting oceanic lithosphere. So the oceanic plate is going to subduct or go below the continental plate. Then you have some volcanoes happening, right? That's what's supposed to happen in a subduction zone. But look at where these volcanoes are. Notice that they're the first mountain range you get to from the coast. This is not true for Washington State. In Washington State, the first mountain range you get to are the Olympic Mountains. And these mountains are not at all volcanic. Not a single volcano among the Olympic Mountains. So what's going on that's different in Washington State? Well, let's finish up Convergent Zone first. So here we have the ocean versus continent. Continent wins. The oceanic crust is going to go below the continental crust. We have earthquakes, lots and lots of earthquakes, from shallow to deep. We have volcanism happening. This is going to be andesitic volcanism. So we get this water mixing with the mantle. And it's going to have some medium thickness, not the super thick, but not real thin. And this rises to the surface, and we have this nice volcanic arc here. What's happening in the Pacific Northwest is that while the Juan de Fuca plate is subducting or going underneath the North American plate, it actually sticks to the lip of North America. And as it sticks to the lip of North America, it uplifts the Olympic mountain range. It also scrapes some seafloor sediments and things, but now we're uplifting that part of the plate. And by uplifting that part of the plate, we build mountains. So those mountains are not at all volcanic. This is just uplifted crust, right? So uplifted crust here, and then you see also that it explains why we have a low point here for the sound. This is where the sound is coming from. The whole Willamette Valley, this low part here, is coming from this idea that we're catching part of the plate on the subducting plate. It gets stuck, and then it uplifts the outer part. We get some scraping, we get some seafloor stuff going on, and then we have this low point in between, and then the volcanism would happen over here. Now notice also in this animation that it gets stuck for a while as this thing is subducting, and then it thrusts forward very quickly. Now this is not a fault in the animation. This is something that could actually happen. It could come to a point where it will break free and thrust forward. This is called a mega thrust earthquake. It would be a huge earthquake. And something, if you want to look up more about this, you could look up the Cascadia megathrust. And there's a lot of information out there about this megathrust earthquake. It's crazy cool, but totally devastating. Wegener guy, he wasn't so crazy after all. He was right. He did come up with a theory. He came up with this theory of plate tectonics, and even though it was not accepted at the time, even though that people did not believe that the continents could actually move, he was right, and he had enough evidence to back it up, and then we have subsequently found more evidence that shows that yes, plates do move. When they interact, catastrophic things happen. Earthquakes, volcanoes, etc. And we can see evidence of those catastrophic events and evidence of the organisms. And these two pieces of evidence, these many pieces of evidence, helped Wegener piece together his theory of continental drift and helped subsequent researchers figure out that yes, indeed, these are the reasons for the earthquakes and volcanoes that we have here on Earth. That's been today's digital replay. Thanks for watching. If you have questions, comment below, send me an email, or see me in class. We'll see you next time.